Hi, everybody. Welcome back. Today, we're going to be talking about a super important concept for linear algebra, and this is going to be the basis of a vector space. So let's not waste any time. Let's write the definition of a basis. So we're going to let V be a vector space. Then the set containing V1, V2, all the way up to Vn, subset of V, is a basis for V if, and we have two criteria we have to meet. One, the span of V1, V2, up to Vn is equal to V. And two, the set of V1, V2, up to Vn is linearly independent. So big idea is the basis should be, or a basis should be like the most concise collection of vectors that we need in order to define our set, right? That was our big picture idea. It's the like essential pieces to define what your vector space is going to be. So to help us achieve that, that's why we have these two criteria here. So we need the span of this collection of vectors to be our vector space. Otherwise, it wouldn't define the whole vector space, right? So that's why we need the span to be the whole vector space. And we want that collection of vectors to be linearly independent, so we don't have any extraneous vectors. We don't have any vectors that we don't need. As a reminder, linearly independent, we can think of that in two ways. Our big picture way of thinking about that was to say you can't write one vector in terms of any of the others. So that's why we want it to be linearly independent, right? So we don't have any unnecessary vectors that we don't need. Or you can think of it as any linear combination of those vectors that equals 0 means that you need 0 of each vector, right? There's only the trivial solution to that. So what we're going to do is we're going to do an example to see if a collection of vectors that I provide for you is a basis for one of the vector spaces we already know and love. So I'm going to erase this definition, write the example on the board, and then we will work through it. All right, here we go. So this is example 19, and it's pretty simply stated, right? Is this collection of vectors a basis for P2? That's it. So in order to answer this question, we have to show first that the span of this set of vectors is going to equal all of P2. And then we have to show that they're linearly independent. If one of those two things fails, then we are not a basis. So it's pretty clear that this set is contained in P2, or the span of the set's contained in P2, because it's going to be all degree 2 or lower polynomials. So we can already see that this set and its span is contained in P2. So really, to show that it's equal to P2, we just have to show that P2 is contained in here. In other words, if I give you any polynomial, we can find a way to express it in these three vectors. So that's going to be our first step. So step 1 is we need to show that the span of x squared plus x, x minus 1, and 1 equals P2, right? And it's clear that the span of these vectors, x squared plus x, x minus 1, and 1, is a subset of P2. So we just have to show containment in the other direction. So we have to show that P2 is a subset of the span of these three vectors. There we go. So to do that, I'm going to start out with an arbitrary polynomial and see if I can write it as a linear combination of these vectors, right? So I've got ax squared plus bx plus c, and I'm trying to write that as a linear combination of these three. So to do that, I'm going to reach into the Greek alphabet for some coefficients. I'm going to use alpha x squared plus x plus beta x minus 1 plus delta 1. Now, our goal is if I were to give you a specific polynomial, so if I were to tell you a, b, and c, you need to be able to tell me the corresponding alpha, beta, and delta. So if we had formulas for alpha, beta, and delta in terms of a, b, and c, we'd be able to do that. You'd be able to, like if I said a is 5 and alpha was the same as, I don't know, a plus 1, you'd be able to say, oh, okay, well, we'll need 6 of this and so on. So that's what we're going to do. We're going to see if we can define alpha, beta, delta in terms of a, b, and c. In order to do that, I need to group my x squareds, my x's, and my constant terms together. So I'm going to keep my ax squared plus bx plus c on the left. On the right, this is the only x squared term, so I'm going to get alpha x squared. Then for the x term, I see that I'm going to get an alpha x and a beta x. So that means I'm going to get alpha plus beta x. And then for the constant term, I see that I'm going to get minus beta plus delta. Now I'm condensing a couple steps here. If you want to write that out, if you want to do the distribution and then the regrouping, absolutely feel free to do that in 2 steps. I'm just trying to save some space on my whiteboard. If that gives you any clue as to how long these problems are going to take us typically. So next I have a series of equations so that A is going to have to equal alpha. A is alpha. B is going to be alpha plus beta. And then C is negative beta plus delta. Now from this, remember, we're trying to get the Greek in terms of the normal alphabet. So we have alpha equaling to A. So I can substitute that into here. If B is A plus beta, and I can subtract A to get a definition for beta. So let's do negative A plus B is beta. And now that I have a definition for beta, I can substitute that in here and figure out a definition for delta. So C is going to equal the negation of beta. So that means A minus B plus delta. Let's bring those two over here. So we're going to get negative A plus B plus C is delta. So what we've done is if I give you a specific polynomial, ax squared plus bx plus c, you can tell me the specific coefficients I need of these 3 vectors to write that polynomial in terms of those 3 vectors, in terms of that set. So therefore, let's write that. So I've got ax squared plus bx plus c is going to equal alpha, which is just a, times this first vector, x squared plus x, plus, then we had beta times the second vector. So beta is negative a plus b, times our second vector, x minus 1, plus delta times 1, but delta is negative a plus b plus c, times 1. Therefore, P sub 2 is a subset of the span of these vectors, since we can write any polynomial as a linear combination of them. It was pretty clear that we had containment in P2. Now we have P2 contained in the span. So therefore, P2 is equal to the span of this collection of vectors. Woohoo, we got the first part done. So we took this whole board space, even writing small, to show that, yep, the span of the set is equal to the vector space we're interested in being. So we know that we've got the space covered. Now we have to say, is this space linearly independent, or are these vectors linearly independent? Are they like the smallest core of what's essential, or do we have some overlap somewhere? So let's erase this and do part 2. Let's see if these are linearly independent vectors. It's a shame all this glorious work being reduced to crumbled dry erase crumbles dust here. 2. So are these vectors x squared plus x, x minus 1 and 1, linearly independent? I'm going to use Li to represent linearly independent because I don't feel like writing those long words today. So to see if they're linearly independent, we have to find our linear combination of them, set it equal to 0, and see, do we get any non-trivial solutions? If not, good to go. If we get any parameters for our solutions, not linearly independent, therefore not a basis. So I'm going to do, let's stick with alpha, beta, and delta. So we'll do alpha x squared plus x plus beta x minus 1 plus delta times 1 equals the 0 polynomial, which is 0x squared plus 0x plus 0. And we're going to do the same thing we did before, except now instead of a, b, and c, we just have zeros as our coefficients. So we're going to get still just alpha x squared. And then we have plus alpha plus beta x. And then we have plus, we're going to get negative beta plus delta times 1. Cool. And yeah, and then we're just going to set each of those equal to 0. So I'm going to get alpha is equal to 0. Alpha plus beta is equal to 0. And negative beta plus delta is equal to 0, right? Those are our coefficients for each of these terms. Well, I know that alpha is 0, so that tells me here that beta is going to be 0. But beta being 0 is telling me here that delta is equal to 0. So again, we have a homogeneous system here, which you could set up a matrix to solve, but if you have one of the variables equal to 0 and you can kind of whittle it down a little bit before you set up a matrix, you may not even need to. So like here, we didn't have to. Here, we can see that alpha has to be 0, beta's got to be 0, and delta has to be 0. So there are no non-trivial solutions. Therefore, the set is linearly independent. So we saw that the span was the space we needed it to be, and that the vectors are linearly independent. So we don't have any, redundancies built into the set. So therefore, this set, x squared plus x, x minus 1, and 1 is a basis for P2. Hooray! We found a basis. And it only took us 2 whole boards worth. It's great. So now that we've got our basis set, let's look at a few theorems and definitions to kind of build on this idea. So I'm going to erase the board and write a couple theorems, and then we'll talk about them. All right, so here are our 2 theorems to look at. So this first one is called the exchange theorem. And it says, let's say you've got a linearly independent set of m vectors. You get like 5 vectors, right? But they're linearly independent. And let's say that every single one of those vectors is in the span of these other vectors. And we don't know how many there are, but we know that it could potentially be a different amount. Then the number of v vectors, the number of linearly independent vectors that we had, is going to be less than or equal to these vectors here. That's because we know that these are linearly independent. Ooh, excuse me. These are linearly independent, so we know we don't have any redundancies. We don't know that information about the w's, so we could have some redundancies here. So we could have some like extra vectors that we don't really need in order to define the set. That's why we have that m is less than or equal to n. Now, the exchange theorem is not going to be so extremely important for our like day-to-day use, but it is extremely important for this theorem, which is going to be really important for our day-to-day use. So the exchange theorem is used to help us out with theorem 12. And theorem 12 says, let's say I have a vector space and I have 2 bases for it. So we've got B and fancy B, and these are not the same. So we did an example where we proved that one basis for P2, right? We found one collection of vectors it could be, but there's nothing saying there can't be a different collection of vectors and maybe even a better collection to use. So what this is saying is if I have 2 different bases, if B has m vectors in it and fancy B has n vectors in it, then they actually have the same number of vectors. So if I have a basis for a vector space that's got 8 vectors in it, and you have a basis for the vector space that has 6 vectors in it, and it's the same vector space, one of us is wrong. Okay, so our vectors, our basis has to have the same number of vectors, no matter what that basis is, which is really nice because when we have something like that happening, we get to define it. So let's define that. That's going to be called the dimension of our vector space. So let's erase the board and define dimension. So this is definition 10. A vector space of V has dimension n if it has a basis consisting of n vectors. And we would write, looks like dim of V equals n. So the dimension of our vector space will equal n. So we had an example where we saw that x squared plus x minus 1 and 1 is a basis for P2, right? So we saw that in our last example. So for this example, which is example 20, teeny tiny 20 there, let's state the dimension of P2. So the dimension of P2 is equal to, well, we had 1, 2, 3 vectors in our basis. So it's a 3-dimensional space. Now, if we wanted to find a simpler way of expressing a generic polynomial in P2, there's a much easier basis to use. And this is often like the standard basis that would be used is we have something x squared, we have something x, and then we have a constant term. So this would be like the standard basis. For P2. Okay, So this would make it a lot easier to kind of check, write our linear combination. Polynomials are linear combinations of these kinds of terms. And you'll notice that in order to have a degree 2 polynomial, we actually need 3 elements in our basis. That's because we need a degree 0 term. Okay. So in general, PK has dimension k plus 1. So the dimension of PK is going to be 1 bigger than whatever that highest degree is. So yeah, so we have a standard basis for our k degree or lower polynomials. Let's talk a little bit about the vectors in Rn. So like those column vectors and row vectors, what would be a standard basis for Rn? Let's define that. So this is going to be definition 11. We're going to let E sub I be an element of Rn. Be the vector in which the ith entry is 1, and all other entries are 0. Then the set E1 up to En is called the standard basis. Of Rn. So, for example, we'll call this example 21. The standard basis of R3 is, and now we're going to define each of these EIs. So E1, because we are in R3, we're going to have a 3 by 1 vector here. E1 has a 1 in the first spot and 0s everywhere else. E2 is going to have a 1 in the second spot and 0s everywhere else. And E3 is going to have a 1 in the third spot and 0s elsewhere. So that's our standard basis for R3. If I wanted to look at, say, the standard basis for, I don't know, let's go with R5. Now, we are going to have not just a 3 by 1, but because we're in R5, we're going to have 5 by 1. And we'll have 1 followed by 4 zeros. And then we'll have 0, 1, and then 3 zeros. And then 0, 0, 1, 0, 0. 0, 0, 0, 1, 0. And then starting with 4 zeros and then a 1. So in R5, this would be E1, E2, E3, E4, E5. So you can see your definition of like E2 is going to change depending on whether you're in R3 or R5 or R207, right? The big picture idea of it is In E2, the second coordinate is 1 and everything else is 0. So here, E2, the second coordinate's 1, everything else is 0. And this makes a really easy basis for R because, for instance, if I have the vector, let's use R3 just as the example, but if I have the vector -7, 2, 6, it's really easy to write it as a linear combination of the standard basis elements. It's going to be -7 times E1 plus 2 times E2 plus 6 times E3. So we don't have to really do all that alpha, beta, delta, whatever business, because this is an easy basis for us to use because it's just defining one coordinate at a time. Also, what this helps us to see is the dimension of Rn, which we probably already know from calculus. But if we look at what's going on here, with R3, we have 3 basis elements because we need to define each of those 3 coordinates. For R5, we have 5 basis elements because we needed to define each of the coordinates for R5. So what that means is if I have Rn, it's going to have dimension n. So yeah, so that's example 22 in our notes. Is just that the dimension of Rn is going to be n. So I'm not going to write that down, but make sure you write it down. The dimension of Rn is n. To close out this video, I think this is going to close us out for this one. Yeah. We're just going to state 3 theorems. That's all, just 3 theorems. So actually, yeah, give me a moment to write these on the board and then we'll talk through them. I mean, it's going to be a moment for me, but it's going to be like an instant for you. TV magic, y'all. Okay. All right. So here are our 3 theorems that I mentioned. So the first one, theorem 13, says that let's say I have a subspace that is not just the 0 subspace of our vector space V. And let's say that V has a finite dimension. So in this course, we're only really going to be worried about finitely dimensional vector spaces. Then W has a basis with n or less vectors. So basically what theorem 13 is stating is that if you have a subspace, it can't have a bigger dimension than its parent space, whatever space it lives in, right? So it could have the same dimension, but it can't have a larger dimension than the world in which it inhabits. So if it has a basis, it can't have more basis elements than its full parent space would have. That's what theorem 13 states. Theorem 14 says that if I have a vector space of dimension n and I have a subspace of V, then the 2 spaces are going to be equal if and only if their dimensions are equal. So in fact, if I were in this situation and I had exactly n vectors, then the subspace would be the parent space. That's what theorem 14 is saying. If I have fewer than n vectors in my basis, or if my dimension is smaller than n, then I'm a proper subspace. I don't have like the whole vector space. And we can apply these theorems to make some conclusions about vector spaces in Rn in particular, especially because we now know that Rn has dimension n, right? So we have these following 3 properties. So if I have a linearly independent collection of n vectors, then it's a basis for R. This is because we know that Rn has dimension n. So any basis is going to have n linearly independent vectors in it. If I have n vectors, then their span is going to be all of Rn, because that's how big its basis was, right? So yeah, so that's, sorry, the heater turned on and it like threw my brain off for a moment. I don't know why. But anyway, yeah, so if we have a linearly independent set of vectors that is the same amount as our dimension, then it's a basis for that set. If now here it's Vm, it's not n, and I don't know if these are linearly independent or not. So if I have a collection of vectors that span all of Rn, then I know that I have to have at least n elements. I can have more because there's nothing here saying that they're linearly independent. So that's kind of applying theorem 13 here to, oh, no, I lied. I lied, ignore what I just said there, okay. So, so this is not applying theorem 13, but this is basically saying like, I have to have at least the basis number of elements if I'm going to span the whole thing. And then I could have more because I could have some redundancies built in. That's what the second one is saying. And then what this third one is saying is that if I have n vectors that span all of Rn, then that set of vectors is linearly independent. It is possible to have n vectors that don't span Rn. Like you could have, like if I'm thinking like R2, I could have the vector 1, 0, and then the vector 2, 0. That would be a collection of 2 vectors, but it doesn't span all of R2 because the second coordinate was 0 for both of those. So I couldn't get any vector that has a non-zero element there. So it's possible to have a linearly dependent collection of n vectors. But if that collection spans all of Rn, so you get everything, then it is going to be linearly independent because it's going to be a basis. So yeah, so that's it for this video on basis. In our next video, what are we going to look at? Oh, we're going to look at some basis some more. Basically, what we're going to do is we're going to say, okay, let's say I'm in this situation for theorem 13 where I have less than n vectors. So let's say I'm a subspace and I have fewer than my whole vector space dimension numbers of vectors in my basis. How can I take a subspace basis and figure out what I need to add to it to expand to the whole big space? What would I need to do in that situation? So that's pretty much what we're going to be looking at in the next video. So I hope you have a wonderful day until then. And yeah, have a good day and I'll see you in the next video. Bye.